Types of solutions. There are a lot of different types of solutions. You can have any combination of phases. We tend to think of a solid dissolved in a liquid, but you can have a gas dissolved in gas. An example of that is air. A gas dissolved in liquid, soda, anything that is fizzy. You can even have a solid dissolved in solid. So if you think about many of the metals that we use are not pure elements. Like stainless steel is not iron. It's a mixture of a bunch of different things. Brass and pewter are not elements, they're mixtures. The gold that's used in rings is not pure gold because pure gold is too soft and would not hold up very well. So they mix other things in it. So as an example, brass is actually a solution of copper and zinc and other things. So in an aqueous solution, the water is the solvent. Okay, so aqueous, water is the solvent, and the solute could be a liquid, a gas, or a solid. Now, we learned, I forget which chapter it was, but we learned some solubility rules. We learned that not all substances will dissolve in water, which is a good thing, because, then the next rain and the whole planet would dissolve. Not so good. So when we talk about solubility, we're talking about the amount of substance that will dissolve in a given amount of solvent. And so this can be expressed with different units. The degree of solubility depends on this tendency towards mixing, and it also depends on the types of intermolecular forces. We learned in chapter 12 that polar compounds are more likely to dissolve in polar solvents and nonpolar in nonpolar. And that's what it's talking here about the types of intermolecular forces. Well, many physical systems tend towards lower energy. You think about a ball rolling down a hill, right? Everything's going to lower potential energy. Well, when you make a solution, that doesn't necessarily lower the potential energy of the particles in the solution. So why does it happen if there is no lowering of energy? Here we're looking at two gases in a chamber that's separated by a barrier. There's argon here and there's neon here. We pull this barrier out and imagine what the gas particles do, right? They travel in a straight line until they bump into something. And so these guys are going to mix together very quickly, much more quickly than the salt water and the fresh water. So it's spontaneously going to form this uniform solution, and yet there's no lowering of potential energy, so there must be something else that is causing this to happen. And that is entropy. So entropy is a measure of the energy randomization or the energy dispersal in a system. So as in that last example, when two ideal gases mix, the kinetic energy of each gas gets spread out over a larger volume. So before, the neon was confined to this volume, and so its energy was confined to that volume. When we allow them to mix, now the neon has spread out. Come on, pointer. And the energy is dispersed over a larger volume. So that's an increase in entropy. Entropy is often thought of as the degree of randomness, and there are some ways in which that is appropriate as well. But substances mix because of this pervasive tendency for energy to spread out whenever it's not restrained from doing so. Entropy also explains the transfer of thermal energy from hot objects to cold ones. You put, I don't know, what would be, you put some ice in a cup of coffee, right? So the potential energy, the kinetic energy, the thermal energy of the coffee is higher than that of the ice cube. And that energy can spread into the ice cube, and now it has been dispersed, and that's an increase in entropy. For those of you watching at home, we've been counting trains, and our record is 11 trains over the course of lab and lecture, which is just ridiculous. Thank you for closing the door so you can hear me. Okay, so intermolecular forces are a big deal in solution formation, and they can promote the formation or prevent the formation. So here, looking at types of intermolecular forces, again, dispersion forces. So heptane and pentane are both nonpolar molecules. They have the same type of forces. They'll probably mix together pretty well. Here we're talking about polar molecules. We've got that dipole-dipole force. Here we have polar molecules with, how do we remember? Phone home. So this is phone home. Fluorine, oxygen, or nitrogen bonded to hydrogen. And then we have the ion dipole forces. So when we try to make a solution, there are intermolecular forces between the solvent molecules. There are intermolecular forces between the solute particles, and there are intermolecular forces between the solvent and the solute. So we use this phrase, like dissolves like, to help us predict things that will be soluble in each other. And this tells us that if the solute and solvent have similar intermolecular forces, a solution will probably form. So in some ways I think of the types of intermolecular forces as being like what language these different molecules speak, right? So if the blue ones here were my ancestors who all came from Sweden and spoke Swedish, and the red ones here are my husband's ancestors that all came from Japan and spoke Japanese, would they mix and mingle very well at a party? No, because they would not understand each other. So the natural thing is you're going to talk to people whose language you understand, right? So if these have different types of intermolecular attractions, they're probably not going to mix together. And we learned this word, miscible. That describes two liquids that are soluble in each other in all proportions. So we can look at the strength of the interactions. So if the solvent-solute, this is so hard to say, solvent-solute interactions are stronger than those between the solvent molecules and the solute molecules independently, then a solution will form. If they're about the same, a solution will form. If those formulas, where did that come from? If these interactions are weaker than those, a solution may or may not form. Depends on how much weaker they are. So here, if the new interactions are weaker, that means this process of mixing is going to cause the energy to go up. And that's not something that spontaneously happens. But if entropy, that tendency of spreading, is great enough, that can overcome the fact that the energy is higher. Okay.
You said that when I said it is less, it would increase the energy?
Well, things are trying to go to lower potential energy, right? Yeah, it's that negative stuff, easy to twist. Okay, determine whether each compound is soluble in hexane. Okay, what's hexane? It's a compound. Excellent. What kind of a compound? What elements does it have? Carbon and hydrogen. Great. We don't actually need to know how many there are. Hex says 6. Yeah. So this is 6 carbons and then enough hydrogens to make all the carbons happy. Is that a polar or a nonpolar substance? It's going to be nonpolar because carbon-hydrogen bonds are nonpolar. If all the bonds are nonpolar, then the substance must be nonpolar. So this is nonpolar. So we're looking at, are these compounds soluble in hexane? What are we looking at? We're looking at, is this molecule nonpolar or polar? Well, what's water? Water's polar. So this is not soluble in hexane. How about ammonia?
Non-polar. Because NH3. Don't you need another one now?
But we have a lone pair on the nitrogen.
So then it is.
So it is, yeah. So this is also polar, so not soluble. How about propane? Oh, look, it's all just carbons and hydrogens also. So this is soluble in hexane. And what about hydrogen chloride? That's also polar, so not soluble. So this is why I wanted you to learn those rules, my two little cheater kind of rules. Substance is nonpolar if there's no lone pairs on the central atom and all the atoms bonded to the central atom are the same. Works about 95% of the time. You don't have to go look up electronegativities. You don't have to necessarily draw the Lewis structure and figure out what the shape of it is and add up vectors. Okay?